So just a quick recap. We have the rules of borrowing. For borrowing, 3 rules. 2 or more pointers access the same data. This is the data race. Okay. So yeah. Ownership. Ownership rules. Each value in Rust has a variable that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. This is the ownership rules. Okay. One owner at all time. If it goes out of scope, the value is dropped. Next, there was rules for references. Any given time, you can either have one mutable reference or any number of immutable references. And references must be valid. That is, owner has not gone out of scope yet. Okay, slice type. Another data type that does not have ownership is the slice. Does not have ownership. Slices let you reference contiguous sequence of element in a collection rather than the whole collection. Here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word. So the entire string should be returned. Let's think about the signature for this function. So it takes a string, reads a string. So assume that it doesn't consume the string. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return an index of the end word. Let's try that. Index of the end word. So usize unsigned, yeah. Let bytes be s as bytes. For I and item, this is okay, and bytes.iterable.enumerate. So okay. Item, if item is equal to the space, we return I. So this is returning, yeah. Index of the end of the word. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes using the asBytes method. Asbytes. Create an iterator over the array using the iter method. Okay. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the result of iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple just like everywhere else in Rust. So in the for loop, we specify a pattern that has I for the index for the tuple and the reference item for the single byte in the tuple. Because we get a reference to the element from .iter.enumerate, we use AND in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal. Byte literal syntax. If we find a space, we return the position. If we find a space, we return the position. Otherwise, we return the length of the string by using s.len. We now have a way to find out the index of the end of the first word in the string, but there is a problem. We're returning a usize on its own, but it's only a meaningful number in the context of a string. Otherwise, in other words, because it's a separate value from string, there is no guarantee that it will be valid in the future. Still be valid in the future. Consider the program for uses first word function. Okay, string hello world and first word, and then we clear the string. This program compiles without any error and would also do so if we used word after calling s.clear, because word isn't connected to the state of s at all. Word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word, but this would be a bug because the contents of s have changed since we saved 5 in Word. Having to worry about index in Word getting out of sync with data is tedious and error prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Now, this and this second word. Now we're tracking a starting and an ending index, and we have more values that were calculated from data in a particular state but aren't tied to that state at all. We now have 3 unrelated variables floating around that need to be kept in sync. String slices. A string slice is a reference to part of a string, and it looks like this. S be the string, hello world, hello be S from 0 to 5, world is S from 5 to 6. This is similar to taking a reference to the whole string, but with the extra 0 to 5 bit rather than a reference to the entire string. It's a reference to a portion of the string. We can create slices using range within brackets by specifying starting index and index, where starting index is the first portion of the slice and the index is one more than the last portion of the slice. Internally, the slice data structure stores the start position and the length of the slice, which corresponds to ending index minus starting index. So in case let world be SX 6 to 11, world would be a slice that contains the 7th byte, counting from 1 of the with the length of 5, length value of 5. Hello world S is this world. Yeah, len 5. Okay. With Rust range syntax, if you want to start at first index 0, you can drop the value before the to period. In other words, these are equal, yeah. Okay. You can also drop both values and take less lines and understand that these are equal. 0 to len, this. String style, okay. Is this equivalent to without this? No, string style indicates that indices must occur at valid UTF character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. A more thorough discussion of UTF handling is in storing UTF in encoded text with string. With all information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written and str. And stir. Is this okay? So is okay, that's weird. And stir is the string literal, isn't it? Let bytes as bytes, and we have return from the beginning to this. Otherwise, return everything. We get the index. That's a strange syntax to just. Okay. I don't like having exceptions in the language design just to accommodate a certain data type. Okay, we get the index in the end of the word in the same way we did in listing for 7. By looking for the first occurrence of a space, we find space and return a string slice using start of the string and the index of the space at the starting and ending indices. Now we call first word, we get a single value that is tied to the underlying string. The value is made up of a reference to the starting point of the slice and number of elements. That means, since if the slice is available, no mutable. Yeah, no mutable. And the number of elements is okay. Turning a slice would work for a second function. Yeah. We now have straightforward API. That's much harder to mess up because the compiler will ensure that references into the string remain valid. Remember the bug in the program listing for 8 when we got index to the end of the word but cleared the string to our index was invalid? Yeah. That code was logically incorrect, but it didn't show any intermediate error. The problems would show up later if you kept trying to use this first word with an emptied string. Slices make this bug impossible and let us know we have a problem with our code much sooner using sliced version of our throw compiler error. Yeah, so immutable, I cannot do any read operation, right? Immutable borrow occurs here. Cannot borrow S as immutable because it is also borrowed as immutable. immutable borrow later used here. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take immutable reference. Because clear needs to truncate the string, it needs to get immutable reference. Rust disallows this and computation fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. String literals are slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. Let s equals hello world. The type of s here is and stir. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. Okay, so it's not and stir is an immutable reference. Okay, yeah, so that makes sense now. String slices as parameter. Knowing that you can take slices of literals and string values lead us to one more improvement on first word. So this is and string. A more experienced Rustacean would write the signature shown instead because it allows to use the same function on both and stir and string literal values. How? Like this. Oh, yeah, this, yeah. Okay. That's nice. If we have string slice, we can pass directly. If we have a string, we can pass a slice of the entire string. Defining a function to take a string slice instead of a reference makes our API more general and more useful without losing any functionality. Okay, other slices. String slices, as you might imagine, are specific to strings, but there is a more general slice type too. Consider this array 1, 2, 3, 4, 5. Just as we might want to refer to part of a string, we might want to refer to part of array. We'd like this a 1, 2, 3. So what's the type of slice? This slice type has type end of array 32. It works the same way as string slices do by storing reference to the first element and length. You will use this kind of slice for all sorts of collection. Yeah, we'll discuss these collections in detail and talk about vectors in chapter 8. Summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. Rust language gives you control over your memory usage in the same way as other systems programming language, but having the owner of the data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust works, so we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping piece of data together in a struct. Okay. Yeah, quick. Using structs to structure related data. A struct or structure is a custom data type that lets you name and package together multiple related values that make up a meaningful group. If you're familiar with our object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples and with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with the struct's data. Structs and enums, discussed in Chapter 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust's compile time checking. Compile time type checking. Okay. Just a moment. Okay. Defining and instantiating structs. Structs are similar to tuples, which were discussed in chapter 3. Like tuples, the pieces of a struct can be different types. Unlike tuples, you will name each type of each piece of data so it's clear what values mean. As a result of these names, structs are more flexible than tuples. You don't have to rely on the order of the data to specify the access of the access value of the access the or access the value of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of a piece of data being grouped together. Then, inside curly braces, we define names and types of pieces of data, which we call fields. For example, listing 5.1 shows struct that stores information about user account. Username, string. Email, string. Sign-in account, signing count, U64. Active boolean. To use the struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then curly brackets containing key value pairs, where the key are the names of the fields and the values of the data we want to store these fields. We don't have to specify the fields with the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template with particular order to create values of the type. For example, we can declare a particular user as shown. Let user1 be user, email, string from whatever, name, string from whatever, active, true, sign 1. To get a specific value from a struct, you could use the dot notation. If we wanted to use the username email, user1.email, wherever we wanted to use this value. If the instance is mutable, we can change value by using the dot notation and assigning a particular field and assigning into a particular field. Let mutable user, user1.email, Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any exception, we can construct new instance of the struct as the last expression in the function body to implicitly return that new instance. User email, return user. It makes sense to name the function parameters with the same name as but having to repeat email, username, fields, variables is a bit tedious. If struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. Using the fields in each shorthand when variables and fields have the same name. Because the parameter's name and struct field are the same syntax, listing 5.4, we can use the field in each shorthand syntax to rewrite build user so that it behaves exactly the same, doesn't have the repetition of email. Okay. Creating new instance user struct. Okay. Email. Sure. Creating instance from other instances with struct update syntax. Yeah, this is the way, and dot user one. Okay. This is fills in from user one. Okay. Using tuple structs without named fields to create different types. Tuple structs. Ah. You can also define structs that look similar to tuples, called tuple structs. Tuple structs have the added meaning, the same added meaning the struct name provides, but do not have names associated with their fields. Rather, just have the types of the field. Tuple structs are useful if you want to give a whole tuple a name and make the tuple. So it's like name tuple with tuple structs. Okay. Struct color, struct point. Okay. Note that black and origin are different types because they are instances of different tuple structs. Each struct you define is its own type, even though the fields within the struct have the same type. For example, a function that takes parameter of type color cannot take point as an argument. Okay. Otherwise, tuple struct instances behave like tuples. You can destructure them into individual pieces. You can use dot followed by index. Sure. Unit like structs without any field. You can also define structs that don't have any field. These are called define or use. Unit like structs because they behave similarly to okay. The unit type unit like structs can be useful in situations in which you need to implement a trait on some type but don't have any data that you want to store in the type itself. So it's like static methods in a class, and yeah, you don't have. Okay, we discussed traits in chapter 10. Ownership of struct data. In the user struct definition listing 5.1, we used the owned string type rather than the stir slice type. This is a deliberate choice because we want instances of this struct to own all of its data and for the data to be valid as long as the entire struct is valid. It is possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in chapter 10. Lifetimes ensure that data referenced by a struct is valid as long as the struct is. Let's say you store a reference in a struct without specifying lifetimes, like this, which won't work. Struct user and stir. Okay. Function main, yeah. The compiler, yeah. Once you, yeah. The compiler will complain. Expected lifetime parameter. In chapter 2, we'll discuss how to fix this error so you can store references in structs, but for now we'll fix error using own types like string instead of references like stir. Be right back. An example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start with a single variable and then refactor the program until we are using structs instead. Let's make a new binary program. Let's make a new binary project with cargo called rectangles that will take the width and height of a rectangle specified in pixels and calculate the area of rectangle. Listing 5.8 shows a short program with one way of doing exactly that in our project's main. Okay. Now run is 1000. Okay, even though listing 5.8 works and figures out the area of the rectangle by calling area function with each of dimension, we can do better. The width and height are related to each other because together they describe one rectangle. The issue with the code is evident because in the signature width height. The area function is supposed to calculate the area of one rectangle, but the function we wrote has two parameters. The parameters are related, but that's not expressed anywhere in our program. It would be more readable and more manageable to group width and height together. We've already discussed one way we might do that, the tuple type section. Okay, using tuples. Okay, dimension using tuples. That's in one way this program is better. The tuple let us add a bit of structure, and now we're passing just one argument. But another way, this version is less clear. Tuples don't name their elements, so our calculation has become more confusing because we have to index into the parts of the tuple. It doesn't matter if we mix up with their height for area calculation, but if you want to draw a rectangle on the screen, it would matter. We would have to keep in mind width is the tuple index 0 and height is the tuple index 1. If someone else worked on this code, they could have they would have to figure this out and keep it in mind as well. It would be easy to forget or mix up these values and cause errors because we haven't conveyed the meaning of our data in our code. Refactoring with structs, adding more meaning. We use structs to add more meaning by labeling. We can transform tuples using data type with a name for the whole as well as names for the part as shown in listing 510. Okay, let's see. Struct rectangle width U32, height U32. Okay, obviously this has only a reference to, but okay, that's no problem. Here we've defined a struct and named it rectangle. Inside the curly braces, we defined fields width and height. Okay, our area function is now defined with one parameter. Okay, this way main retains ownership and can continue using rect1, which is the reason of the and. Area function accesses width and height of the instance. Our function signature for area now says exactly what we mean. Calculate the area rectangle using width and height, conveys the width and height. Okay, It gives descriptive names to the values rather than using tuple. Okay. Adding useful functionality with derived traits. Okay. It would be nice to be able to print an instance of rectangle while we were debugging our program and see the values for all the fields. Listing 511 tries to using println macro, as you can see. Okay, no, it's a problem. When we compile this code, we get an error. Okay, rectangle doesn't implement display. The println macro cannot. Okay. Println macro can do many kinds of formatting, and by default, the curly brackets still println to use formatting known as display. Output intended or directed end user consumption. The primitive types we've seen so far implement display by default because there's only one way you would want to show a one or any other primitive type but to a user. But with structs, the way println should format the output is less clear because there are more display possibilities. Do you want commas or not? Do you want to print the curly brackets? Should all fields be shown? Due to this ambiguity, Rust doesn't try to guess what we want, and structs don't have a provided implementation of display. If we continue regarding this error, we'll find this helpful note. The trait std is not implemented for rectangle. Note, in format strings, you may be able to use this or this for pretty print instead. Let's try. The println macro can call will now look like it. Okay. Putting the specifier inside the tail tells println we want to use an output format called debug. The debug trait enables us to print out struct in a way that is useful for developers so we can see its value while debugging our code. Compile the code. Okay, drat, we still get an error. Rectangle doesn't implement debug. But again, the compiler gives us a helpful note. std format debug is not implemented for rectangle, and derive debug or manually implement debug. Rust does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do that, we add the annotation derive debug just before struct definition. Okay. The area, the R, the area, oh, come on. Of the rectangle Okay. The area of the rectangle, this is pretty, yeah. Okay. Nice. It's not the prettiest output, but it shows values and all fields of instance, which would definitely help during debugging. When we have larger structs, it's useful to have output that is a bit easier to read. In those cases, we can use instead of this in println string. When we use style, the output would look like this. Okay, Rust has provided a number of traits for us to use with the derive annotation that can be useful, that can add useful behavior to our custom types. Those traits and behavior listed in Appendix C. We'll cover how to implement these traits with custom behavior, as well as how to create your own traits in Chapter 10. Our area function is very specific. It only computes the area of a rectangle. It would be helpful to tie this behavior more closely to our rectangle struct, because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function into an area method defined in our rectangle type. Okay. Here's a small break. Okay, let's see if items have shipped. Amazon. I don't have any, I believe. They're pushing the 3000 more into okay, back. Let's check on Newegg. Okay, reached Portland, Oregon. Okay, let's continue. Wait, I need to check my mail first. Okay, nothing new. Okay, let's continue. Methods are similar to function. They're declared with the function keyword and their name, They can have parameters and a return value, and they contain some code that is run when they're called from somewhere. However, methods are different from functions in that they're defined within the context of a struct or enum or a trait object, which we cover in chapters 6 and 17 respectively. And their first parameter is always self, which represents the instance of the struct method is being called on. Defining methods. Let's change the area function that has rectangle instance as a parameter instead making an area method. Okay, so it's implement rectangle. Implementation of rectangle function area self. Function area self. Function never used area. Rect.area. Is it like this? No. Rect1.area. What's this? Function area itself. Why is it throwing our function area self? Implement rectangle. Function area self. Okay. Self.height. Let's read the error. Warning, function never used area. Dead code by default. But it's used here. Now, still, what? Rust struct method. Oh, wait. This area, yeah. It was correct. 74 might be. Okay. Okay. To define the function within the context rectangle, we start implementation block, then move the area function within the impulse curly brackets and change the first and in this case only parameter to be self and signature and everywhere within the body, where we called area function and passed rectangle as an argument. We can instead use method syntax to call the area method. Okay, method syntax we dot in signature instead of rectangle because Rust knows the type of self is a rectangle due to this method's being inside the implementation of a rectangle context. Note that we still need to put and before self, just as we did in at rectangle method. Methods can take ownership of self, borrow self immutably, as we've done here, or borrow self mutably, just as they can any other parameter. Chosen at self, okay. Same reason we don't want to take ownership and we just want to read the data in the struct and not write it. If you wanted to change instance that we've called method on as part of what the method does, we'd use and at mutable self in the first parameter. Having a method that takes ownership of the instance by using just self as the first parameter is rare. This technique is usually used when the method transforms self into something else and you want to prevent the caller from using the original instance after the transformation. Yeah, you want to consume the self. I'm guessing drop does that. The main benefit of using method instance of function, in addition to using method syntax and not having to repeat the type of self in every method signature, is for organization. We've put all things we can do with instance of type implement block rather than making future users of our code search for capabilities of rectangle in various places in the library we provide. Where's the arrow operator? In C and C++, two different operators are used for calling methods. You use dot if you're calling a method on the object directly, and arrow if you're calling a method on a pointer to the object, and need to dereference the pointer first. In other words, if object is a pointer, object arrow something is similar to dereferencing object dot something. Rust doesn't have an equivalent to the arrow operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling methods is one of few places in Rust that has this behavior. Here's how it works when we call method object.something. Rust automatically adds in at mutable or star so object matches the signature of the method. In other words, the following are the same. That makes sense. Okay. The first one looks much clearer. This automatic referencing behavior works because methods have a clear receiver, the type of self. Given the receiver and name of the method, Rust can figure out definitively whether a method is reading self, mutating self, or consuming self. The fact that Rust makes borrowing implicit for a method receives a big part of making ownership ergonomic ergonomic in practice. Methods with more parameters. Multiple implementation blocks. Each struct is allowed to have multiple implementation blocks. Equivalent to the code shown. Okay. There is no reason to separate these methods into multiple implementation here, but this is a valid syntax. We'll see case much more useful in chapter 10. We discuss generic types and traits. Okay. Associated function. Another useful function blocks is that we are allowed to define functions with implementation blocks that do not take self as a parameter. These called are associated function because they're associated with a struct. These are static. They are still functions, not methods, because they don't have instance of a struct to work with. You've already used string from associated function, often used in constructors that will return a new instance. For example, we would provide an associated function that would have one dimension parameter and use that as both width and height, thus making it easier to create a rectangle rather than specifying, okay, square, yeah, return a rectangle, both being size. To call this associated function, we use the colon syntax with the struct name. Let sq square 3. This function is namespaced by the struct. Syntax is used with, okay. Last part. So associated functions are like static methods. Methods with more parameters. I guess I'm moving. If I do 4 chapters a day, so yesterday I did until chapter 4. What if I do 5, 6, 7? So 5, 6, 7, 8. Yeah. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This is one day. This is another day. This is one day, we said. 17, 18, 19, 20. 16, 15, 14, 13. 12, 11, 10, 9. Okay. So I have to finish up till chapter 8 tonight. 5, 6, 7, 8. Yeah. Methods with more parameters. Let's practice using methods by implementing a second method rectangle. This time we want the instance to take another instance rectangle and return true if the second rectangle can fit completely self. Otherwise, it should return false. Easy. Yeah. No, I'm not gonna do it. Anyhow, it's easy to see. Yeah. Methods can take multiple parameters. Sure. How does it look like? Okay, one, two. Limitation. Look, the method name can hold. Take immutable, borrow another rectangle. We can tell the type of the parameter by looking at the code. Okay, rect1 can hold rect, passes it to immutable. And then write which would mean immutable borrow. You want main to retain ownership. Okay. Can hold boolean, sure. Structs let you create custom types that are meaningful for your domain. By using struct, you can keep associated pieces of data connected to each other and name each piece to make your code. Let's let you specify behavior. This is okay. Structs aren't the only way you can keep. Okay. Minimum features. Enums. We'll finish chapter 6 and do okay, we'll finish chapter 6 and it's category theory. Okay, let's continue. This chapter will look at enumeration, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching and match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how flet construct is another convenient and concise idiom available to handle enums in your code. Enums are a feature in many languages, but their capabilities differ in each language. Rust's enum are most similar to algebraic data types in functional languages such as F#, OCaml, and Haskell. Defining enums. Let's look at a situation we might want to express code and see enums useful more appropriate than struct case. Say we need to work with an IP address. Currently, two major standards we use version 4 and 6. There are only two possibilities. An IP address will would come. We can enumerate all possible variants, which is an enumeration of its name. Any IP address can be either version 4 or version 6, but not both at the same time. The property IP address makes the enum data structure appropriate because enum values can only be one of its variants. Both versions 4 and 6 addresses are still fundamentally IP addresses, so they should be treated as the same the code handling situation that apply Anki. Okay. Can express the concept by defining an IP address kind, enumeration and listing possible kinds. An IP can be version 4, version 6. These are variants for enum. Okay, enum, IP address kind, version 4, version 6. IP address kind is now a custom data type that we can use elsewhere in our code. Can create instances of each of the two variants IP address kind like this for IP address kind v4 6 v6. Note that variants new space under its identifier. We can use double colon, separate colon. The reason this is useful is now that both are the same type IP address kind. Can then instance and define function that takes any IP address kind can call this function with either variant, route. Yeah. Using enums has even more advantage. Thinking more about our IP type at the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structs, you might tackle this problem as shown in listing 6.1. So you do the enum and struct kind and then add a string and then home. Yeah, here we've defined struct IP address that has two fields, kind, yeah, two instances of this, home, and second just loop back variant IP address. Okay, can represent the same concept in a more concise way with using the enum rather than an enum inside a struct by putting data directly into each enum variant. This new definition, IP address enum, both v4 v6 variants have associated string values. Okay. We attach each variant of the enum directly, so there is no need for an extra struct. There is another advantage using enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type addresses always have 4 numeric components that have as 0 and 55. If you wanted to store v4 address as 4 u8 values, but still express v6 as one string value, wouldn't be able to do the struct. Enum handles this case with ease. We've shown several different ways to define data structures to store versions 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are so common, the standard library has a definition we can use. Let's look at how the standard library defines IP address. Has exact enum and variants that we've defined and used, but it embeds the address data inside variants in the form of two different structs which are defined different. Struct IP address, yeah. Enum IP address, either v4 with a struct, v6 with a struct. This code illustrates that you can put any kind of data inside an enum variant, string, numeric types, structs, for example. You can even include another enum, also standard library types, often not much more complicated than you might come up with. Even though standard library contains definition of IP address, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope. We'll talk more about bringing into scope in chapter 7. Let's look at another example of the enum listing 6.2. 6.2 message quit move to a certain location, right, message enum, move anonymous struct inside it. Defining an enum with variants such as one listing, okay, except enum doesn't use the struct. All variants are grouped together under message. The following struct could hold the same data preceding enum, okay. Few structs with each, we couldn't as easily define a function to take care of these kinds of message, as we could use message defined, implement message, call self, body would be defined here, let message write, string from hello, m.call. Okay, the body of the method would use self to get the value that we called on this method. In this example, we've created a variable m that has value message.write string from hello, and that is self. Okay, call runs. Let's look at another enum in the standard library that is very common and useful option. The option enum and advantages over null values. In the previous section, we looked at how IP address enum lets us use Rust type system to encode more information than just the data our program. This section explores a case study of option, which is another enum defined by standard library. The option type is used in many places because it encodes the very common scenario in which a value could be something or could be nothing. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have null feature that many languages have. Null is a value that means that there's no value. In languages with null, variables can always be in two states, null or not null. 2009 presentation, non-references, the $1 billion mistakes. Tony Hoare, the inventor of null, has this to say: I call it my $1 billion mistake. At the time, I was designing the first comprehensive type a system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performance automatically by a compiler. But I couldn't resist the temptation to put a null reference simply because it was so easy to implement. This has led to innumerable errors, vulnerability, system crashes, which have probably cost billions of dollars of pain and damage in the last 40 years. The problem with null values is that if you try to use a null value and not as not null value, you will get an error of some kind because this null or not null property is pervasive. It's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null value is a value that is currently invalid or absent for some reason. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but does have an enum that can encode the concept of value being present or absent. The enum is option T, as defined by the Rust standard library as follows: enum option T sum T, none. Option T enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. In addition, so are its variants. You can use some and none directly without the option prefix. The option t enum is still just a regular enum, and some t and none are still variants of type option t. The T syntax is a feature of Rust we haven't talked about yet. It's a generic type parameter, and we'll cover generics in more detail in chapter 10. For now, all you need to know is that T means some variant of the option can hold one piece of data of any type. Here are some examples of using option value, hold number types. Okay, sum 5, sum string, option none. If we use none rather than some, we need to tell Rust what type of option we have because the compiler cannot infer type of some invariant. Some variant will hold. Okay. When we have some value, we know that a value is present, and the value held with the sum. When we have a non-value, in some sense, it means the same as null. We don't have a valid value. Why is having option any better than having null? In short, because option and t, where t can be any type or different types, the compiler won't let us use option t as value if it were definitely a valid value. For example, as if it were, I8 equals 5. Option I8 sum 5. Let sum equals x plus y. Let's create an error message. Okay. Intense, no implementation of I plus. Okay. In effect, this message means that Rust doesn't understand how to add an I8 and an I8 option I8, because they are different types. When we have value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having a check for null before using that value. Only when we have an option or whatever type value we're working with do we have to worry about possibly not having value, and the compiler will make sure we handle that case before using the value. In other words, you have to convert option t to t before you can perform t operations with it. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Not having to worry about incorrectly assuming not null value helps you be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the value type of the value is option t. Then you use that value. You are to use that value when you use you are required to explicitly handle the case when the value is null. Everywhere that a value has type that isn't an option t, you can safely assume the value isn't null. This was a deliberate design decision for Rust to limit the null's pervasiveness and increase the safety of Rust code. So how do you get t out of some variant when you have value of type option t? So you can use the value. The option t enum has a large number of methods that are useful for a variety of situations. You can check them out in its documentation. Becoming familiar with the methods on option t will be extremely useful in our journey. Is it like result? There's expect or accept, sorry. Is there accept? Is some? Is none? Contains? As ref? As mutable? As pin? Expect. consuming the self value, panics if the value none. Yeah, it's like in general, in order to use, you want to have a code that will handle each variant. You want some code that will run only have some t value and the code is allowed to use inner t. You want to you want some code run if the non-value and that code doesn't have t available. The match expression is a control flow construct that does just this when used with enums. It will run code, different code depending on which variant of the enum it has, and that code can use data inside the matching value. Okay. So far, so good. Small break. Okay, we continue. The match control flow operator. Rust has an extremely powerful control flow operator called match that allows you to compare a value against a series of patterns and then execute the code based on which pattern matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all different kinds of patterns and what they can do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms all possible cases are handled. Think of match expression as being like a coin sorting machine. Coin slides down a track with variously sized hole along it. Each coin falls through the first hole that it encounters that fits into. In the same way, values go through each pattern in a match, and at the first pattern, the value fits, the value falls into associated code block. Okay, because we mentioned coins, let's use them as an example match. We can write function, take known, unknown United States coin, and okay. I just need to compile this as cargo build. Dead code, but okay. Yeah. Okay. Let's break down the match. Next match arms. Okay. Operator separates. Match. Okay. can have curly brackets. Patterns that point to values. Okay, did I debug? US state. Quarter state, and the state is here. Okay. Value in cents. Colon, Alaska, US state Alaska. Colon would be, yeah. Matching operator with T. Here we have none, sum I plus 1, sum I plus 1. Okay, keeps none. Okay. Matches are exhaustive. Okay. This is match against an enum, find a variable, execute. It's a bit tricky. First, you get used to it. Okay. Matches are exhaustive. There's one other aspect of match that we need to discuss. Consider version plus 1. Yeah, this will be an error. Placeholder. The rest, yeah. Do nothing, basically. Yeah. Match expression can be a bit wordy. Flet. Yeah. Some value. We want to have some value. 0u8. What is 0u8? Oh, 0 byte. If let sum 3 equals some value. Okay. We want to do something with some 3 match, but nothing. Yeah. Yeah. If it's equal to let so we could write if let, okay, text pattern and expression and separate by equal sign. It works the same as match. Yeah. First arm. Yeah. Let mutable count. Okay, count plus 1. Summary: if you have a situation in a program is too verbose. Okay. Flet only works with Oh, this or. Huh. Is it or? What is Rust if lit Rust bar or? Doesn't show. I don't know. Okay. We're done with the first. Okay. Okay. Can stop here for now and continue later on. Okay, it's only 2 pages, but the remaining ones are small. Okay. But then this is humongous chapter. But yeah. Okay.